What if I told you there are objects out there in the cosmos moving so fast they could cross the entire United States in less time than it takes to blink? We're talking speeds so unimaginable they make the fastest fighter jets look like they're standing still. Picture this, a cosmic bullet tearing through space at over 1,000 kilometers per second. That's not science fiction, that's the universe showing off. Now, think about the fastest thing you've ever seen, maybe a bullet train, a lightning strike, or even a rocket launch. But here's the thing, compared to some of the speed demons lurking in the depths of space, those are like watching paint dry. Imagine an object so fast it could circle the Earth 7 times in just 1 second. Or a star hurtling through the galaxy with enough velocity to escape the gravitational pull of an entire supermassive black hole. These aren't just random facts, they're glimpses into the extreme physics that govern our universe, where speed isn't just about moving quickly, it's about breaking every rule we thought we understood. And that's exactly what we're diving into today. Over the next few minutes, you'll discover 30 mind-bending facts about the fastest objects in the cosmos, from hypervelocity stars ejected by galactic collisions to particles accelerated to nearly the speed of light in the hearts of dying stars. Each one of these cosmic speedsters tells a story about the forces that shape our universe, the violent events that launch them into motion, and the sheer, jaw-dropping power of physics pushed to its absolute limits. So buckle up, because we're about to take a ride through the fastest, most extreme corners of the universe, where the laws of speed and motion as we know them get rewritten in ways you won't believe. One of the most extreme speed demons in the universe isn't a spaceship or a rogue planet, it's a city-sized object spinning faster than your blender on its highest setting. When a massive star explodes in a supernova, its core can collapse into something called a neutron star. These remnants are so dense, a single teaspoon of their material would weigh as much as a mountain. But here's the wild part, some of these neutron stars spin so fast they complete over 700 full rotations every single second. That's like a cosmic top whirling at an astonishing 43,000 revolutions per minute. To put that into perspective, if you were standing on the surface of one of these stars, which, let's be clear, would instantly vaporize you, you'd be moving at nearly a quarter the speed of light. How does something that heavy spin so mind-bendingly fast? It all comes down to physics. When a star collapses into a neutron star, it conserves the original star's angular momentum, but now squeezed into an object just 12 miles wide. Imagine an Olympic figure skater pulling their arms in to spin faster, except in this case, the skater is the remains of a star, and the spin is powerful enough to distort space-time itself. Some neutron stars, called pulsars, shoot out beams of radiation like cosmic lighthouses. Because they rotate so quickly, these beams flicker at precise intervals, so regular, scientists once mistook them for signals from extraterrestrial civilizations. That's how extreme these objects are. They're not just fast, they're so unnaturally precise, they blur the line between natural phenomena and something almost engineered. And yet, they're just one example of how the universe takes the ordinary rules of motion and cranks them up to impossible extremes. While neutron stars push the limits of rotational speed, some stars take speed to an entirely different level, escaping whole galaxies altogether. These are hypervelocity stars, stellar runaways rocketing through space at over 1 million miles per hour. To put that in perspective, at that speed you could travel from Earth to the Moon in just under 15 minutes. One of the most famous examples is US 708, a star clocked at nearly 1.6 million miles per hour. How does something so massive get launched like a cosmic bullet? The answer lies in the violent dance around supermassive black holes. When a binary star system, two stars orbiting each other, wanders too close to a black hole's gravitational grasp, one star gets captured while the other gets violently flung away. It's like a slingshot effect on an unimaginable scale, where the escaping star isn't just set free, it's hurled across the galaxy with enough speed to escape its gravitational pull entirely. But US 708 isn't alone. Astronomers have discovered dozens of these rogue stars, each one telling a story of galactic-scale chaos. Some may have been ejected by the collision of two galaxies, where the gravitational turbulence launches stars like debris from a cosmic car crash. Others might owe their speed to the explosive power of a supernova, where the dying star's violent end catapults its companion into the void. What's truly astonishing is where these stars end up. Unlike most objects bound to their galaxies, hypervelocity stars are destined for intergalactic space, hurtling into the vast emptiness between galaxies, where they'll drift alone for billions of years. They're cosmic loners, set adrift by forces so powerful they redefine what we thought possible for stellar motion. And every time we discover another one, it's a reminder that even in the quiet vastness of space, the universe still has ways to surprise us with its sheer, unstoppable velocity. But even hypervelocity stars aren't the fastest things in the cosmos, not even close. For that, we have to look at the most extreme particle accelerators in the universe, relativistic jets. These are narrow beams of superheated plasma screaming from the poles of black holes at nearly the speed of light. Picture a fire hose of energy so powerful it stretches for thousands of light years, far beyond the boundaries of its home galaxy. Take the supermassive black hole at the center of galaxy M87, for example. When scientists captured the first ever image of a black hole's shadow in 2019, they also observed its jet, a searing beam of particles stretching 5,000 light years into space. The material in that jet isn't just moving fast, it's hitting speeds of 99% the speed of light. That means if you could ride a single particle in that jet, time would slow down so dramatically for you compared to the rest of the universe. A single minute on your watch could equal years back on Earth. How does a black hole launch something with that much energy? It all comes down to twisted magnetic fields and insane gravitational forces. As matter spirals into the black hole's accretion disk, a superheated ring of gas and dust, some of it gets funneled toward the poles. There, the black hole's rotation and its monstrous magnetic fields act like a cosmic railgun, twisting and accelerating particles until they're shot into space at nearly light speed. Some quasars, extremely bright galactic cores powered by supermassive black holes, have jets so energetic they outshine their entire host galaxy. What's truly mind-blowing is how durable these jets are. Unlike a burst of energy that fades quickly, some relativistic jets remain stable for millions of years, carving through intergalactic space like a laser through fog. They can even shape the evolution of entire galaxy clusters, heating surrounding gas so much that it prevents new stars from forming. So while black holes are famous for sucking things in, their jets prove they're just as good at hurling matter across the universe at speeds that push the very limits of what physics allows. And every time we spot one of these cosmic particle cannons, we're witnessing the universe's most extreme form of power, raw velocity harnessed on a galactic scale. Ever seen a cosmic cannonball? Some pulsars don't just spin, they rocket through space at over 1,000 kilometers per second, leaving glowing trails in their wake. Take the pulsar in the Guitar Nebula, a celestial speedster racing so fast, its shockwave has sculpted the surrounding gas into the shape of a giant interstellar guitar. But how does something as dense as a neutron star, packing the mass of our sun into a city-sized object, get launched like a bullet? The answer lies in the chaos of its birth, a supernova explosion so violent it doesn't just destroy the star, it gives it a kick strong enough to escape entire star clusters. When a massive star goes supernova, the explosion isn't always symmetrical. Imagine a balloon popping. If one side bursts slightly before the other, the recoil sends it flying in the opposite direction. Now scale that up to a stellar explosion with the energy of 1 billion suns. If the supernova's collapse is lopsided, whether from uneven magnetic fields or turbulent jets of neutrinos, the newborn pulsar gets a staggering push, like a rifle firing a cosmic bullet. Some of these recoiling pulsars hit speeds so high, they'll eventually break free from the Milky Way altogether, destined to drift forever in intergalactic space. The Guitar Nebula pulsar isn't just fast, it's a time capsule. The glowing wake it leaves behind, shaped by its supersonic motion, tells the story of its journey. As the pulsar plows through interstellar gas, it rams into particles like a speedboat slicing through water, creating a bow shock that heats the gas until it glows. Over thousands of years, these trails fade, meaning every one we spot is a fleeting snapshot of a pulsar's incredible velocity. And here's the wild part: asymmetrical supernova might be more common than we thought. That means the cosmos could be littered with these runaway pulsars, invisible to us until their trails dissipate into the void. What's truly humbling is the force behind these kicks. A typical pulsar recoil carries the energy of 100 octillion nuclear bombs, enough to fling an object heavier than our Sun at a fraction of light speed. Yet even that pales in comparison to the forces that shaped it. Every fleeing pulsar is a relic of a star's final, violent act, a reminder that in the universe, even death can be a launchpad. Black holes are the ultimate cosmic anchors, so massive, not even light can escape their grip. But what if I told you some of these gravity monsters are actually racing through space like intergalactic drifters? Take Jero J1655540. A black hole clocked at 250,000 miles per hour, fast enough to cross the entire Atlantic Ocean in just 20 seconds. How does something with the gravitational pull of a collapsed star get moving that fast? The secret lies in cosmic chaos. When two black holes spiral toward each other and merge, the explosive energy of their collision can kick the newborn black hole clear across the galaxy. It's like firing a cannon, except instead of gunpowder, the force comes from ripples in space-time itself. During the merger, gravitational waves carry away enormous amounts of energy in one direction, launching the remaining black hole in the opposite direction with enough force to escape entire star clusters. But spotting a runaway black hole isn't as simple as seeing it zip across the sky. Since black holes are, well, black, astronomers have to detect their motion indirectly through the glowing wreckage they leave behind. As Jero J1655540 plows through space, its superheated accretion disk, the swirling ring of doomed matter circling it, gets stretched into a lopsided comet-like tail. The faster the black hole moves, the more distorted this disk becomes, creating telltale signatures in the X-rays it emits. Here's where things get even stranger. Some models suggest these rogue black holes might be far more common than we realize. When galaxies collide, central supermassive black holes can engage in gravitational slingshot battles, flinging each other into the void. And unlike hypervelocity stars, which eventually slow down, a black hole's momentum is nearly unstoppable, its path only altered by the rarest, most massive objects in its way. What's truly haunting is where these runaway black holes end up. Unlike stars, they don't glow, meaning one could be drifting silently through our galactic neighborhood right now, invisible until it distorts the light of a background star or tears apart a passing comet. Every time astronomers find another one, it's a humbling reminder. Even the universe's most dominant forces aren't immune to becoming cosmic fugitives, hurtling through the darkness with nothing but gravity and sheer, unstoppable speed. Most planets take months or even years to orbit their stars, but not Kepler 70b. This scorching world races around its sun so fast, a full year passes in less than 6 hours. That's not a typo. While Earth leisurely takes 365 days to complete its journey, this planet hustles through an entire orbit faster than you might finish a work shift. What makes Kepler 70b such a speed demon? It all comes down to proximity. This planet orbits so close to its star, you could fit the entire distance between them inside our own sun. If you stood on its surface and somehow survived, the star would dominate the sky, appearing over 30 times larger than our Sun does from Earth. That proximity also means gravitational forces have locked the planet in a death grip, with one side permanently facing the star while the other stares into eternal darkness. But here's where things get truly extreme. Those same gravitational forces don't just keep the planet in place, they're actively tearing it apart. As Kepler 70b whips around its star at nearly 500,000 kilometers per hour, tidal forces stretch and compress its interior like molten taffy. The resulting friction heats its surface to a staggering 7,000 degrees Celsius hotter than some stars. To put that into perspective, iron doesn't just melt here, it boils into vapor. The planet's dayside isn't just a scorching wasteland. It's a swirling ocean of vaporized rock and metal, where entire mountain ranges might evaporate into the atmosphere over centuries. And the night side, while slightly cooler, it's still hotter than lava flows on Earth, with supersonic winds likely racing across the Terminator line to redistribute the unbelievable heat. What's fascinating is how this planet defies expectations. Astronomers once assumed nothing could survive so close to a star, yet Kepler 70b persists, albeit as a grotesque, semi-molten relic of what might have once been a gas giant. Its breakneck orbit offers a glimpse into the violent endgame of planetary evolution, where a world doesn't just die quietly, it races toward oblivion in a blaze of unimaginable heat and speed. Every time we find a planet like this, it's a reminder that the universe doesn't just play by the rules, it rewrites them in fire. The Milky Way might look serene from our vantage point, but make no mistake, it's a cosmic carousel spinning at mind-bending speeds. Here's the puzzle. Stars near the galaxy's outer edges whip around at 540,000 miles per hour, faster than our solar system's relatively leisurely 490,000 miles per hour. And this isn't just a fun fact, it's a violation of everything Newton's laws predict. Think about a playground merry-go-round. The farther out you sit, the harder you have to hold on to avoid flying off. That's basic physics. Outer objects should move slower to stay balanced against gravity's pull. Yet in our galaxy, stars far from the center orbit just as fast as those closer in, as if the merry-go-round's edge were spinning just as violently as its center. For decades, this flummoxed astronomers. How could gravity alone explain stars moving this fast without the entire galaxy flinging itself apart? The answer lies in the invisible scaffolding holding galaxies together, dark matter. This mysterious substance doesn't emit light or interact with normal matter, but its gravitational grip is the only thing keeping those outer stars from sailing into the void. Imagine wrapping the Milky Way in a ghostly web, one we can't see, but whose presence is undeniable based on how it bends the motion of everything within it. Without dark matter's extra pull, those edge-of-the-galaxy stars would be moving hundreds of thousands of miles per hour slower, just like Newton's equations suggest. Here's where things get even stranger. Our solar system, tucked about halfway between the center and the edge, orbits at a mere 490,000 miles per hour. That's still fast enough to cross the continental United States in under 10 seconds, but it pales next to those outer stars. This speed gap hints at dark matter's uneven distribution, like an invisible sphere encasing the galaxy, its density increasing toward the edges to give those stars an extra gravitational kick. What's wild is how much we still don't know. Dark matter remains one of cosmology's biggest mysteries, and these rogue orbital speeds are our best clue to its presence. Every time astronomers measure another star defying Newton's predictions, it's a reminder that the universe is far weirder and faster than our textbooks ever imagined. And somewhere out there, invisible threads of dark matter are pulling the strings, orchestrating this high-speed galactic dance we're only beginning to understand. We've seen stars and black holes racing through space at unbelievable speeds, but what about something even smaller? Imagine a single subatomic particle, tinier than an atom, screaming through the cosmos so fast it makes light seem sluggish. Meet the "oh my god" particle, a proton detected in 1991 that was traveling at 99.99999999999% the speed of light. That's not a typo. This particle was so ludicrously fast it missed matching light speed by less than a trillionth of a percent. To grasp how absurd this speed is, consider this. If a proton moving that fast raced a beam of light across the entire Milky Way, the light would win by just a fraction of a millimeter. The energy packed into this single particle was equivalent to a baseball hurled at 90 kilometers per hour, except instead of a ball, it was something a quadrillion times smaller. How does the universe even accelerate something so tiny to such mind-bending velocities? The leading suspect, active galactic nuclei, the supermassive black holes at the hearts of galaxies, surrounded by swirling disks of superheated plasma. These cosmic power plants can channel particles along their magnetic fields like a railgun, accelerating them to near light speeds. But here's the catch. Even the most powerful black holes shouldn't be able to produce particles as energetic as the oh my god particle. That's led scientists to consider even wilder possibilities: colliding galaxy clusters, where shockwaves from merging gas clouds could act like natural particle accelerators, or decaying relics from the early universe like cosmic strings left over from the Big Bang. What's truly bizarre is how these particles reach us. Cosmic rays like the oh my god proton travel for millions or even billions of years across space, dodging magnetic fields and interstellar gas, only to slam into Earth's atmosphere with enough force to trigger a subatomic avalanche. When they hit, they create showers of secondary particles so vast they can spread across several square kilometers, all from one proton's worth of energy. Yet for all their speed, these particles carry a mystery. Unlike light, which points back to its source, cosmic rays get scrambled by magnetic fields during their journey, making it nearly impossible to trace their origins. The oh my god particle could have come from anywhere: a nearby quasar, a long-dead star, or something we haven't even discovered yet. Every one that strikes Earth is a messenger from the universe's most violent events, carrying clues about forces so powerful they turn specks of matter into the fastest objects in existence. And with each detection, we're reminded that even the tiniest things in the cosmos can defy our understanding of speed, energy, and the limits of physics itself. After witnessing the universe's natural speed demons, from runaway pulsars to particles hitting near light velocity, you might think human engineering couldn't possibly compete. But here's the twist: we've actually built something that comes shockingly close. NASA Parker Solar Probe currently holds the record for the fastest human-made object ever, clocking in at an astonishing 430,000 miles per hour. That's fast enough to zip from New York to Los Angeles in under 20 seconds. How did we pull this off? The secret lies in an ancient celestial maneuver: gravity assists. Instead of relying solely on rockets, the Parker Solar Probe slingshots around Venus, using the planet's gravity like a cosmic slingshot to steal speed with each pass. But the real magic happens when it dives toward the Sun, where our star's monstrous gravity yanks the probe faster and faster, like a roller coaster plummeting down its steepest drop. At its closest approach, the probe skims just 4 million miles above the Sun's surface, closer than any spacecraft has ever dared, enduring temperatures hot enough to melt steel while collecting data that could revolutionize our understanding of solar winds and space weather. Now here's the cosmic irony: as impressive as 430,000 miles per hour sounds, it's still a tortoise compared to the hairs of the universe. The hypervelocity star US 708, for example, moves almost 4 times faster. Even the slowest neutron star spins at a rate that would leave the Parker probe looking like it's standing still. It's a humbling reminder that while human ingenuity can push the boundaries of speed, nature routinely operates on a scale that dwarfs our greatest achievements. But don't dismiss the Parker probe as just a speedy underdog. What it lacks in raw velocity compared to cosmic phenomena, it makes up for in precision and endurance. While a pulsar's speed is the result of chaotic stellar death, the probe's trajectory is a masterpiece of orbital calculus, a dance of mathematics and engineering refined over decades. Every time it whips around the sun, it's not just breaking speed records, it's decoding the very forces that govern the fastest objects in the universe. So next time you hear about a hypervelocity star or a relativistic jet, remember, we might not hold the universal speed title, but we're getting closer to understanding the rules of the race. And in the grand scheme of things, that's just as revolutionary. When a star reaches the end of its life in a cataclysmic supernova, it doesn't just fade away, it detonates with enough force to briefly outshine entire galaxies. But the real shockwave comes after the initial flash, as the explosion's debris blasts outward at a staggering 30,000 kilometers per second. That's fast enough to cross Earth's entire diameter in less than a tenth of a second. Take Cassiopeia A, the remnants of a star that exploded around 300 years ago as observed from Earth. Even now, its shockwave races through space at hypersonic speeds, expanding a shell of superheated gas over 10 light-years wide. What makes these shockwaves so extraordinary isn't just their speed, it's how they reshape the cosmos around them. As the supernova's debris plows into nearby clouds of gas and dust, it doesn't just scatter them. It compresses and heats the material like a cosmic snowplow, triggering chain reactions that birth new stars. Imagine flicking a whip so hard the crack ignites fires in its wake. That's essentially what's happening on a stellar scale. In Cassiopeia A's case, astronomers have spotted dense knots of gas along the shockwave's edge, each one a potential nursery for future stars squeezed into existence by the explosion's fury. But here's the twist: not all shockwaves are destructive. While the inner layers of the supernova churn with turbulent, scorching debris, the outer shock front acts like a sculptor. By the time it reaches interstellar clouds, it's often slowed just enough to gently compress rather than obliterate. This delicate balance between annihilation and creation is why supernovae are considered cosmic recycling plants. The same explosion that tears a star apart also sows the seeds for its successors, enriching nearby gas clouds with heavy elements like iron, gold, and uranium that weren't there before. What's truly remarkable is how long these shockwaves persist. Even centuries after the initial blast, Cassiopeia A's expanding shell continues to forge new physics in its wake. The shock front's collision with interstellar material generates X-rays and radio emissions so intense, they serve as natural laboratories for studying particle acceleration. In some regions, electrons spiral along magnetic fields at near light speed, creating brilliant synchrotron radiation that outshines the remnant's own glowing debris. It's a reminder that a supernova's death isn't an endpoint, it's a transformation where raw speed and energy rewrite the rules of an entire stellar neighborhood for millennia to come. In the cosmic dance of gravity, few pairs move with the blistering speed of Cancri, two white dwarfs locked in an orbital embrace so tight, they complete a full revolution every 5.4 minutes. That's faster than the average pop song. These stellar corpses, each about half the mass of our sun but squeezed into an Earth-sized sphere, whip around each other at 1.8 million miles per hour. At that speed, they could lap the moon's orbit around Earth in just 20 seconds. What makes this binary system so extreme? It's all about proximity. The two white dwarfs orbit so closely, their surfaces would almost touch if placed in our solar system, roughly the distance from New York to Boston. That nearness means gravity isn't just a gentle tug here, it's a vice grip warping space-time itself. As they spin, their colossal masses create ripples in the fabric of the universe, gravitational waves that carry energy away, slowly but inevitably tightening their spiral. Here's where the real cosmic drama unfolds. Over millions of years, those gravitational waves will sap the system's energy, dragging the stars closer until they finally collide. When they merge, the resulting explosion could unleash a supernova, or, depending on their combined mass, collapse into a neutron star. But until then, H.M. Cancri serves as a living laboratory for testing Einstein's theory of relativity. The star's breakneck orbit causes their light to Doppler shift dramatically, one dimming as it races away from us, the other brightening as it streaks toward us like a celestial lighthouse flickering at hyperspeed. What's truly mind-bending is how this system defies intuition. Two objects with the mass of dead stars, moving fast enough to cross the continental US in under a second, yet locked in a waltz so precise, their orbital period is measurable down to the millisecond. It's a reminder that even in death, stars can create some of the universe's most spectacular performances where gravity writes the choreography, and speed becomes the rhythm of destruction. Most galaxies spin like whirlpools, with stars slowing down as you move outward, but NGC 1277 laughs in the face of cosmic convention. This spiral galaxy, located 220 million light-years away, has stars racing around its core at a jaw-dropping 2 million miles per hour. That's roughly 3 times faster than our Sun moves through the Milky Way, and it defies everything we know about galactic physics. The reason for this absurd speed. A central black hole so monstrous, it makes Sagittarius, a star the Milky Way's own supermassive black hole, look like a lightweight. While most galaxies have black holes accounting for about 0.1% of their mass, NGC 1277's behemoth makes up a staggering 14% of its entire mass. Imagine if our Sun suddenly ballooned to 90 times its size. That's the kind of gravitational dictatorship this black hole exerts over its galaxy. What's truly bizarre is how this affects the galaxy's rotation curve. The graph astronomers use to map how stars move at different distances from the core. In normal galaxies, stars farther out orbit slower, like cars on a highway gradually easing off the gas. But NGC 1277's rotation curve is flat as a ruler. Whether a star is right next to the black hole or halfway to the galaxy's edge, it's hauling just as fast as if some invisible hand keeps flooring the cosmic accelerator. This isn't just a quirk, it's a glimpse into how galaxies might have behaved in the early universe, where black holes grew first and galaxies formed around them like moths to a gravitational flame. While most galaxies today have had billions of years to settle into balanced systems, NGC 1277 seems frozen in time, a relic of an era when black holes ruled with unchecked might. And here's the kicker, this speed comes at a cost. The galaxy's outer stars are moving so fast they should have escaped entirely, yet somehow they haven't. That means NGC 1277's grip on its stars isn't just strong, it's borderline tyrannical, bending the rules of motion to keep everything locked in this high-speed cosmic dance. Every time we study this galactic oddball, it forces us to rethink just how much influence a black hole can wield, and how violently the universe can rewrite its own laws. Quasars are already among the brightest objects in the universe, but SDSS J1106 + 1939 takes cosmic violence to another level. At its core, a supermassive black hole feasting on surrounding matter unleashes winds so powerful, they fling gas clouds into space at 5,000 kilometers per second, fast enough to cross the entire United States in under 2 seconds. These aren't gentle breezes, they're supersonic tsunamis of superheated plasma, carrying enough energy to reshape entire galaxies. What's shocking is how these winds form. As material spirals into the black hole's accretion disk, friction heats it to millions of degrees, creating pressures so intense they blast gas outward like a cosmic pressure cooker exploding. But here's the twist, these winds don't just dissipate harmlessly, they collide with surrounding star-forming gas at velocities so high, they strip galaxies of the very material needed to create new stars. In SDSS J1106's case, its winds dump the equivalent of 400 solar masses of gas into space every year, enough to starve a galaxy of its future. Yet this destruction serves a purpose. Without these winds, galaxies would grow unchecked, their central black holes gorging until they choked on their own sprawl. By ejecting gas at such extreme speeds, quasars like SDSS J1106 act as cosmic regulators, balancing growth against chaos. It's like a self-cleaning oven. The same forces that could obliterate everything instead create equilibrium, ensuring galaxies don't burn too bright or collapse under their own gluttony. The sheer scale of these winds defies imagination. They stretch for thousands of light years, their shockwaves etching intricate patterns in the interstellar medium. Some astronomers believe they might even seed neighboring galaxies with heavy elements, spreading the building blocks of planets and potentially life far beyond their origins. So while these quasar winds appear destructive, they're also sculptors, shaping the universe in ways we're only beginning to understand. Every time we observe one, we're witnessing a black hole's paradoxical role, destroyer, architect, and cosmic janitor all at once. Imagine a world with no sunrise, just endless night, drifting through the frozen void of interstellar space at 500,000 miles per hour. That's the reality for planets like PSO J318.5-22. Cosmic orphans ejected from their star systems with such violence, they'll never know the warmth of a sun again. These rogue planets don't just move fast, they're among the most isolated objects in the galaxy, untethered from any star's gravity, doomed to wander the darkness forever. How does a planet get banished so brutally? The answer lies in gravitational chaos. When young planetary systems form, they're crowded and unstable. Think of a celestial game of pinball where gas giants like Jupiter wield enough gravity to send smaller neighbors careening. If two massive planets pass too close, one can slingshot the other outward with enough force to escape the star's pull entirely. For PSO J318.5-22, that moment of exile happened early. Astronomers estimate it's been drifting solo for roughly 12 million years, barely colder than the stars it left behind. What's chilling about rogue planets isn't just their speed, it's the eerie environments they carry. Without a host star, their surfaces plunge to temperatures near -250 degrees Celsius colder than Pluto. Any atmospheres they once had likely froze solid, collapsing into icy wastelands where methane and nitrogen snowdrifts might tower over barren rock. Yet there's a twist. Some could harbor hidden oceans beneath their frozen crusts, kept liquid by tidal forces or radioactive decay. These subsurface seas, insulated by miles of ice, might even cling to heat for billions of years, offering bizarre oases in the void, the most haunting part. These worlds are practically invisible, unlike planets orbiting stars which reveal themselves by the light they reflect. Rogue planets emit only faint infrared whispers, the residual warmth of their violent birth. That's why PSO J318.5-22 was spotted only because it's unusually bright for its age, still glowing from the energy of its formation. Most rogue planets are undetectable with current technology, meaning we're likely surrounded by countless unseen wanderers, each one a frozen testament to the chaos of cosmic evolution. But here's the kicker: these nomads might not be entirely lifeless. Some astrobiologists speculate that rogue planets with subsurface oceans could, against all odds, harbor extremophile microbes, organisms clinging to geothermal vents in perpetual darkness. If life exists there, it would thrive in total isolation, cut off from the rest of the universe, evolving under ice sheets where no light ever penetrates. It's a staggering thought. The fastest, loneliest worlds in the galaxy might also be silent arcs, carrying the possibility of life into the infinite black. Gamma-ray bursts are the universe's ultimate fireworks brief, violent eruptions of energy so intense they outshine entire galaxies in seconds. But GRB 080916c wasn't just another burst, it was a cosmic record breaker, blasting jets of plasma at 99.9999% the speed of light. If you could ride one of those jets, time would slow to a crawl. A single second for you would stretch into months for everyone else. The numbers behind this explosion are almost incomprehensible. In less than a minute, GRB 080916c released as much energy as 9,000 supernova combined, enough to outshine every star in the observable universe for those brief moments. What's even wilder is how we can see bursts like this from billions of light years away. That's thanks to a phenomenon called relativistic beaming, where the jet's extreme speed focuses its energy into a narrow beam, like a cosmic flashlight pointed directly at Earth. Without that effect, most gamma-ray bursts would fade into the background noise of the universe, too dim and too brief to notice. But how does something accelerate particles to such unfathomable speeds? The leading theory points to the birth of a black hole. When a massive star collapses, its core doesn't just quietly form a black hole. It convulses, launching twin jets of plasma from its poles at near light speed. These jets aren't gentle streams, they're magnetized whirlwinds, twisting space itself as they plow through the dying star's outer layers. The friction and magnetic fields in this chaos act like a particle accelerator on steroids, revving electrons and protons to velocities that defy physics as we know them. Here's where things get even stranger. Because these jets move so close to light speed, their radiation gets stacked from our perspective. Normally, light spreads out evenly in all directions, but relativistic beaming squashes it into a tight cone. From Earth, that makes the burst appear thousands of times brighter than it would otherwise, like catching a lighthouse beam head-on instead of seeing it from the side. It's the universe's ultimate optical illusion, turning what might have been a faint flicker into a beacon visible halfway across the cosmos. What's truly sobering is the aftermath. Long after the jets fade, the explosion's shockwaves continue carving through interstellar gas, leaving behind glowing remnants that linger for centuries. GRB 080916c's light took 12.2 billion years to reach us, meaning we're witnessing a cataclysm from a time when the universe was barely a fifth of its current age. Every burst we detect is a time capsule from an era when stars died more violently, black holes formed more frequently, and the cosmos was a far more turbulent place. And with each one, we're reminded that even in the vast quiet of space, nature still knows how to throw the ultimate speed freak show. At the heart of our galaxy, where gravity twists space into knots, there's a star that redefines speed. S4714 isn't just fast, it's a cosmic daredevil, screaming around the Milky Way's supermassive black hole at 15,000 kilometers per second. That's 8% the speed of light, or fast enough to cross Earth's entire diameter in less than a second. What makes this star truly extraordinary isn't just its velocity, it's the suicidal orbit that propels it. Most stars near Sagittarius, a star, our galaxy's central black hole, keep a respectful distance. But S4714 takes a different approach. It dives closer than any known star, skimming just 9 billion miles from the event horizon. That's like threading a needle with a comet, considering the black hole's gravity could shred a star twice that distance. This elliptical orbit isn't smooth sailing. It's more like a cosmic roller coaster where the star accelerates to blistering speeds at its closest approach, then slows slightly as it swings outward, only to be yanked back in for another death-defying loop. Here's where physics gets weird. At such extreme velocities, Einstein's relativity comes into play. Time for S4714 ticks noticeably slower than for the rest of the galaxy. A minute here equals about 55 seconds for distant observers. The star's light also battles the black hole's gravity, stretching into longer, redder wavelengths as it struggles to escape, an effect called gravitational redshift. Yet despite these cosmic hurdles, S4714 persists, completing an orbit every 7.6 years with clockwork precision. What's truly baffling is how this star survives. Conventional models suggest such a close orbit should be unstable, with tidal forces tearing the star apart within centuries. Yet S4714 has likely circled Sagittarius, a star for thousands of orbits. Some astronomers speculate it might be the dense core of a former giant star, stripped of its outer layers by repeated black hole encounters. Others think it could be part of a hidden population of compact stars that evolved under these extreme conditions, cosmic masochists thriving where others would perish. Every time S4714 makes its closest approach, it's not just breaking speed records, it's testing the limits of stellar endurance. The friction from plowing through the black hole's accretion disk should slow it down, yet it races on. The gravitational tides should have ripped it apart, yet it holds together. This star isn't just fast, it's a rebel, rewriting the rules of orbital mechanics with every fearless loop around the galaxy's most dangerous landmark. And as astronomers track its path, they're uncovering clues about how black holes shape their stellar neighborhoods, one hypervelocity daredevil at a time. The universe isn't just fast, it's brutal. Take the Bullet Cluster, a cosmic wreck where two galaxy clusters collided head-on at a staggering 10 million miles per hour. But here's the twist: the real action wasn't the galaxies themselves, it was the invisible battlefield of dark matter left behind. When these clusters smashed together, their stars slipped past each other like ghosts, barely slowed by the collision. The hot gas between them, though, slammed together so violently it glowed in X-rays, forming a bullet-shaped shockwave that gives the cluster its name. But the smoking gun, the way gravity itself bent around the wreckage. Astronomers mapped the cluster's mass using gravitational lensing, how its gravity distorts light from background galaxies, and found something bizarre. The bulk of the mass wasn't where the visible galaxies or gas were. Instead, it lurked in two distinct clumps far from the collision's debris. That mismatch is why the Bullet Cluster became dark matter's most famous evidence. Normal matter, the gas and stars we can see, got stuck in the cosmic traffic jam, while the invisible dark matter sailed right through, unfazed. Think of it like two clouds of smoke passing through one another. The smoke particles, normal matter, collide and slow down, but the wind carrying them, dark matter, keeps blowing undisturbed. The dark matter's gravity was so strong, it warped space-time more than all the visible material combined, proving it wasn't just empty space, it was something real, massive, and utterly invisible. What's wild is how precise the measurements were. By tracking the lensing distortions, scientists calculated the dark matter halos were moving at speeds that would fling a spaceship from Earth to Neptune in under an hour. Yet despite that velocity, the halos stayed gravitationally bound, holding their galaxies like puppets on strings. This wasn't just a lucky snapshot, it was a courtroom-worthy demonstration that dark matter, whatever it is, dominates the universe's structure. The Bullet Cluster isn't just a freak accident. Similar smash-ups have been found, like the Musket Ball Cluster and El Gordo, each showing the same eerie separation of dark and normal matter. Together, they paint a picture of a universe where the stuff we can see is just the tip of the iceberg, and the real heavyweight dark matter calls the shots from the shadows. And every time we study these collisions, we're glimpsing the invisible scaffolding that holds the cosmos together, one high-speed wreck at a time. Some planets don't just orbit their stars, they evaporate before our eyes. Take HD 209458b, a gas giant so close to its sun, its atmosphere is being blasted into space at 35,000 kilometers per hour, forming a tail that stretches over 200,000 kilometers like a comet on steroids. Every second, this planet sheds 10,000 tons of gas, enough to fill a fleet of cargo ships. The culprit, stellar radiation, turned up to 11. HD 209458b orbits 100 times closer to its star than Jupiter does to our Sun. bathing in ultraviolet light so intense it superheats the upper atmosphere to tens of thousands of degrees. At those temperatures, hydrogen gas doesn't just float. It gets catapulted into space, atoms ricocheting off each other with enough energy to escape the planet's gravity entirely. Imagine a bonfire so hot the flames don't just rise, they launch into orbit. This isn't just a slow leak, it's a full-blown atmospheric hemorrhage. The escaping gas forms a swirling plume, illuminated by starlight like a cosmic beacon. Astronomers first spotted it when the planet passed in front of its star. Instead of a clean shadow, they detected a fuzzy trail of gas extending far beyond the planet itself. That tail isn't static, it twists and billows, sculpted by stellar winds into shapes that change by the hour. What's fascinating is how this process reshapes planets over time. Hot Jupiters like HD 209458b might start as massive gas giants, but after billions of years of this stellar bombardment, they could be stripped down to bare, rocky core skeletons of their former selves. Some might even transform into entirely new classes of worlds, Chthonian planets, the ghostly remnants of gas giants that lost their atmospheres to the void. Yet even as HD 209458b crumbles, it teaches us about planetary resilience. Despite losing unfathomable amounts of material, it's held onto its atmosphere for over 4 billion years. That balancing act between stellar fury and gravitational tenacity hints at how planets survive in the universe's most extreme neighborhoods. Every wisp of gas torn away carries clues about the delicate dance between stars and their orbiting worlds, where even the mightiest planets can't always hold on. Most asteroids take years to orbit the Sun, but not 2021 PH27. This scorching space rock screams around our star at 70,000 miles per hour, completing a full lap in just 113 days. That's faster than Mercury, faster than any known asteroid, and so blisteringly quick, its year is shorter than a semester on Earth. What makes this asteroid's speed so extreme? Its orbit is a cosmic tightrope walk, a stretched ellipse that brings it closer to the Sun than Venus at its nearest approach, then swings it out past Mercury's orbit. At its closest point, the rock endures temperatures over 900 degrees Fahrenheit, hot enough to liquefy lead and turn its surface into a temporary lava landscape. Yet just months later, it's racing through the cooler outer stretches of its path like a comet without a tail. The real kicker, this breakneck orbit shouldn't last. With each close pass, solar gravity tugs at the asteroid, slowly altering its trajectory through an effect called relativistic precession, the same phenomenon that made Mercury's orbit puzzle scientists before Einstein cracked it. For 2021 PH27, these tiny shifts add up fast. Current projections suggest it might collide with Venus or Mercury within a few million years, or get flung into the Sun entirely. Until then, it's locked in a high-stakes game of celestial chicken, skimming past solar inferno after solar inferno. What's truly remarkable is how we found it. Unlike most asteroids detected in the calm of night, this one was spotted in twilight glare, a testament to modern telescope sensitivity. Its discovery was sheer luck. Had it been just a few degrees off in its orbit, we might have missed it entirely. Now that we're watching, though, it's giving astronomers a front-row seat to extreme orbital mechanics, where speed isn't just a curiosity, it's a countdown to destruction. Every time this asteroid survives another close encounter, it defies expectations, reminding us that even in a seemingly orderly solar system, some objects live life in the fast lane, right until they don't. On September 14, 2015, humanity heard the universe speak for the first time. The Laser Interferometer Gravitational Wave Observatory LIGO detected a signal so subtle it made the faintest whisper seem deafening by comparison. What they captured was the death spiral of two black holes, each about 30 times the mass of our Sun, circling each other at half the speed of light before colliding in a cataclysm that briefly outshone the entire observable universe. This wasn't just any merger, it was GW150914, the first direct proof of gravitational waves Einstein predicted a century earlier. As the black holes drew closer, their insane velocities warped space-time like a spinning blender, sending ripples across the cosmos at light speed. But here's what makes it extraordinary. By the final milliseconds before collision, the pair whirled around each other 250 times per second, so fast their event horizons stretched into grotesque teardrop shapes. The energy released in those last moments was 50 times greater than all the stars in the universe combined, compressed into a gravitational tsunami that reached Earth a billion years later as a faint, almost musical chirp. That chirp, a rising tone that jumps from 35 to 250 Hz in less than a second, isn't just data. It's the sound of space itself ringing like a bell. When scientists slowed it down, they heard the black hole's final, desperate orbits speeding up as they lost energy to gravitational waves, culminating in that abrupt cutoff, the moment the two became one. The resulting black hole, 62 solar masses, meaning 3 suns worth of mass, vanished, converted entirely into pure gravitational energy. That's the universe's most efficient furnace where even light can't escape, but the vibrations of space itself broadcast the violence to the cosmos. What's haunting is how common this might be. Since GW150914, LIGO detected dozens more mergers, some involving neutron stars, others with black holes far larger. Each has its own unique chirp, a cosmic fingerprint revealing the masses, spins, and final moments of these invisible dancers. And every signal peels back another layer of mystery. How do black holes pair up in the first place? Are they ancient survivors of star clusters or products of previous, even more violent mergers? The answer might lie in the spins. Before colliding, GW150914's black holes weren't just orbiting. They were rotating on their own axes at dizzying speeds, their event horizons dragging space around them like cosmic whirlpools. That spin affects the gravitational wave's shape, imprinting clues about their origins. Some might have been born spinning rapidly from asymmetric supernova. Others could have gained momentum through galactic collisions, like celestial tops wound up by the universe's most violent hands. And as detectors grow more sensitive, we'll hear fainter, more distant mergers, perhaps even the primordial black holes theorized to form in the Big Bang's first second. What's staggering is the scale of these events. That half-light-speed finale wasn't just fast, it was space-time itself being wrung like a wet towel, vibrating at frequencies that shook the entire solar system. Yet the signal that reached us moved LIGO mirrors by less than 1,000th the width of a proton. It's the universe's ultimate paradox, the most violent events imaginable, whispering to us across billions of years through the subtlest tremors in the fabric of reality. And with every new chirp, we're tuning into a cosmic symphony, one where black holes don't just collide but sing. The sun might seem like a steady, unchanging ball of light from our perspective, but beneath its calm surface lies a seething cauldron of magnetic chaos. And when that chaos erupts, it can fling billion-ton clouds of plasma into space at 6 million miles per hour. These coronal mass ejections, or CME, are the solar system's most powerful storms, capable of crossing the 93 million-mile gulf to Earth in less than 18 hours. To grasp that speed, imagine a bullet train racing from New York to Los Angeles in under 2 seconds. The sheer violence behind these ejections comes from twisted magnetic fields. When the sun's tangled loops of magnetism snap like overstretched rubber bands, they release energy equivalent to 1 billion hydrogen bombs, enough to catapult superheated plasma into the void. The fastest CMEs don't just travel, they obliterate the solar wind in their path, creating shockwaves that ripple across the solar system. And when one of these storms takes aim at Earth, the consequences can be catastrophic. History offers a chilling example, the Carrington event of 1859. Back then, telegraph systems were the height of technology, yet when a CME slammed into our planet, operators watched in horror as sparks leaped from their equipment, setting papers ablaze. Auroras, normally confined to polar skies, blazed so brightly over Cuba and Hawaii that people mistook them for dawn. If a storm of that magnitude struck today, the results would be apocalyptic. Modern power grids, satellites, and communication networks, all vulnerable to the surge of charged particles, could fail on a continental scale. Experts estimate a Carrington-level event could black out entire nations for months, triggering trillions in damages. What's terrifying is how little warning we'd have. Despite advances in solar monitoring, we might only have hours between detecting a CME and feeling its impact. Satellites like NASA's Solar Dynamics Observatory provide a crucial heads-up, but shielding Earth's infrastructure from such raw cosmic power remains a monumental challenge. Some countries are hardening power grids and installing surge protectors, while others stockpile transformers in preparation. Yet there's a twist: CMEs aren't purely destructive. These violent eruptions also sculpt the heliosphere, the protective bubble of solar wind shielding our solar system from interstellar radiation. Without them, harmful cosmic rays would bombard Earth unchecked. It's a cosmic balancing act where the same forces that threaten our technology also preserve the delicate conditions for life. Every time a CME races toward us, it's a reminder of our fragile place in the solar system, advanced enough to predict the storm but still at the mercy of the sun's fury. Most celestial objects rotate with a certain dignity, but 2 MSSJ 0348-6022 laughs in the face of cosmic decorum. This brown dwarf, a failed star too small to ignite hydrogen fusion, spins so ferociously, it completes a full rotation in just 1.08 hours. That's faster than a Hollywood action movie, with its equator whipping around at 320,000 miles per hour. To put that in perspective, Jupiter, no slouch itself, takes nearly 10 hours to complete a rotation, its cloud tops moving at a leisurely 28,000 miles per hour in comparison. What makes this speed even more astonishing is the physics at play. Brown dwarfs are already bizarre objects too massive to be planets, yet not quite stars, but 2 MSSJ 0348-6022 pushes the limits further. At that rotational velocity, centrifugal forces are nearly stronger than gravity's grip, stretching the object into an oblong shape like a cosmic egg. If it spun just 10% faster, it would tear itself apart, scattering its material into space in a violent stellar breakup. Scientists first noticed its dizzying speed through subtle changes in its infrared light, a telltale flicker as brighter and darker regions whirled in and out of view. But here's the twist: brown dwarfs usually slow down as they age, like a spinning top losing momentum. So how did this one stay so hyperactive? One theory suggests a traumatic past, perhaps a collision or close encounter with another object that sent it into this frenetic spin, like a cosmic billiard ball struck just right. The implications are staggering. Objects like this challenge our understanding of rotational limits in celestial bodies. Neutron stars spin fast, but they're incredibly dense. Gas giants rotate quickly, but they're fluid. 2 MSSJ 0348-6022 exists in a strange middle ground where the rules aren't as clear. Studying it helps astronomers test models of how angular momentum works in substellar objects, how they form, evolve, and sometimes, like this one, go completely off the rails. And here's the kicker: this brown dwarf isn't alone. More of these ultra-fast rotators are being discovered, hinting at a whole population of cosmic speed demons hiding in plain sight. Each one is a puzzle, a challenge to our assumptions, and a reminder that even in the coldest, dimmest corners of the universe, things can move faster than we ever thought possible. Among the most crowded neighborhoods in the cosmos are hypercompact star clusters, places where gravity packs stars so tightly together they move like swarms of furious bees. Take Messier 80, a dense globular cluster orbiting the Milky Way, where stars average speeds of 100,000 miles per hour. That's 5 times faster than our sun's leisurely cruise through the galaxy, all because these stars are crammed into a space just 100 light-years across. To picture that density, imagine squeezing 1,000,000 stars into a volume where the nearest stellar neighbor would be just a light week away, 30 times closer than Proxima Centauri is to us. In this stellar mosh pit, motion is constant chaos. Stars don't follow orderly orbits like planets in a solar system. They jostle and weave like commuters in a rush-hour subway, their paths constantly bent by close encounters. The cluster's core is especially frenetic, a region where stars zip past each other at such blistering speeds. Gravitational nudges can fling them into entirely new trajectories within minutes. It's a celestial game of pinball where the bumpers are other stars and the prize is survival. This density comes with a violent side effect: stellar collisions. While stars in most of the galaxy pass like ships in the night, in Messier 80, close encounters are inevitable. Every few thousand years, 2 stars get too close, their outer layers tearing away in spectacular tidal disruptions. Sometimes they merge entirely, creating bizarre blue stragglers, stars anomalously young and massive for the cluster's ancient population. These Frankenstein stars shine brighter and hotter than their neighbors, their existence a direct result of the cluster's extreme environment. What's fascinating is how these clusters persist despite the chaos. You'd expect such tight quarters to lead to complete disintegration, but Messier 80 has held together for nearly 12 billion years. The secret lies in its gravitational glue, the combined pull of countless stars and dark matter, creating a deep well that even the fastest stars can't escape. Over eons, the cluster's speed demons do get ejected, but fresh stars spiral inward to replace them, maintaining the frenzy. This isn't just a cosmic curiosity. Hypercompact clusters are time capsules. Their stars are among the oldest in the universe, forged when galaxies were just assembling. By studying their motions, astronomers unravel the early history of the Milky Way, tracing how these dense knots of stars got pulled into our galaxy's orbit. Every close encounter, every collision leaves a fingerprint in the light of these stars, telling stories of a time when the universe was younger, wilder, and far more turbulent than the orderly cosmos we see today. When astronomers first spotted GK Persei brightening suddenly in 1901, they witnessed what they thought was a typical nova, a stellar outburst fading within months. But over a century later, this cosmic explosion is still rewriting the rules, its remnants expanding outward at an unprecedented 1,200 kilometers per second. That's fast enough to cross the continental United States in just 3 seconds, leaving behind a nebula growing visibly larger even within a human lifetime. What makes GK Persei's aftermath so extraordinary is the violence still etched across its debris field. Time-lapse images taken decades apart reveal delicate filaments of gas stretching farther into space with each observation, like a firework frozen mid-explosion. Unlike most nebulae that dissipate gently, this one races outward with enough force to plow through interstellar gas, creating shockwaves that glow in X-rays. The culprit, a white dwarf that stole hydrogen from its companion star until the pressure triggered a runaway thermonuclear reaction, not powerful enough to destroy the star entirely, but relentless enough to keep ejecting material at speeds that dwarf most supernova. Here's where the physics gets wild. The nebula's expansion isn't slowing down as expected. Instead, it's accelerating, fueled by additional outbursts from the white dwarf that continue to inject energy into the system. Imagine a car crash where the wreckage keeps getting hit by more cars, each collision adding fresh chaos to the debris field. That's essentially what's happening here, with the central star periodically reigniting like a faulty engine stuck in overdrive. The most haunting detail lies in the nebula's structure. Unlike the symmetrical rings of most planetary nebulae, G.K. Persei's remnant is a ragged, asymmetrical web, a testament to the turbulence of its birth. Some filaments race ahead like cosmic sprinters, while others lag behind, creating a fractured silhouette against the interstellar backdrop. This irregularity offers clues about the explosion itself, suggesting the nova wasn't a clean detonation but a lopsided convulsion that spat material unevenly into space. What's truly remarkable is how this celestial speedster connects to the bigger picture. Nova like G.K. Persei are cosmic recyclers, scattering heavier elements forged in their furnaces across the galaxy. Every atom of carbon, oxygen, or iron in those racing filaments might one day end up in a planet, or even a living organism. And as we watch this nebula defy expectations, still expanding over a century later, we're witnessing the long tale of stellar evolution where death isn't an endpoint, but a transformation playing out at the edge of physics limits. Imagine two dead stars, each heavier than our sun but crushed into a sphere no larger than a city, whipping around each other so fast they complete an orbit in just 2.4 hours. That's Quasar J0737-3039, a relativistic binary system where pulsars race through space at 1,000th the speed of light. Their motion so precise it's become a laboratory for testing the very fabric of reality. What makes this pair extraordinary isn't just their speed, it's how their dance warps the universe around them. As they spiral closer, their immense gravity distorts space-time, creating ripples that carry energy away as gravitational waves. These waves are so relentless, they'll eventually cause the pulsars to collide in about 85 million years, a blink in cosmic terms. But until then, their orbital decay is a ticking clock, one that matches Einstein's predictions with staggering accuracy. The real magic lies in the pulsars' beams of radiation that sweep across Earth like lighthouse beacons. Because these beams arrive with atomic clock precision, astronomers can track subtle changes in their timing. Every time one pulsar passes behind its companion, its signal delays by a fraction of a millisecond, not because it's moving slower, but because the other pulsar's gravity bends the path of light. This effect, called Shapiro delay, is a direct window into how mass warps space, and Quasar J0737-3039 measures it with error margins smaller than a millionth of a second. But here's where Einstein gets put to the test. According to general relativity, the pulsar's orbits should gradually shrink as they lose energy to gravitational waves. And they do, but not just as predicted. The decay matches Einstein's equations to within 0.0003%, making this system one of the most stringent confirmations of relativity ever found. It's as if the universe itself calibrated these pulsars as a precision instrument, their motion etching equations into the void. What's truly astonishing is how much we've learned from just watching these cosmic metronomes tick. Their spins reveal the star's internal structure, hinting at exotic states of matter denser than an atomic nucleus. Their orbits map the curvature of space-time like a ruler bending around a bowling ball. And their eventual collision will unleash a flash of gravitational waves so powerful, it might momentarily outshine all the stars in the Milky Way. Until then, every pulse from Quasar J0737-3039 is a reminder, even in death, stars can illuminate the deepest truths of the universe. Floating silently between galaxies, the Smith Cloud is a cosmic ghost ship, a vast structure of hydrogen gas stretching over 11,000 light-years, plummeting toward the Milky Way at 700,000 miles per hour. If you were to watch its approach in fast-forward, it would look like a celestial tidal wave, arcing through the void with enough momentum to crush entire star systems. Yet this isn't just another gas cloud, it's a mystery wrapped in hydrogen, carrying secrets about the violent forces that shape galaxies. What makes the Smith cloud so baffling is its sheer speed and trajectory. Unlike most intergalactic gas, which drifts slowly, this behemoth is moving fast enough to escape the gravitational pull of most galaxies. Its path suggests it originated somewhere beyond the Milky Way, possibly as debris torn loose during a long-forgotten collision between smaller galaxies billions of years ago. Some astronomers speculate it could be the remnants of a failed galaxy, a clump of dark matter and gas that never quite ignited into stars, doomed to wander until a bigger galaxy like ours ensnared it. But here's the twist: the cloud isn't just falling blindly. It's leaving a glowing trail like a comet's tail as it rams into the Milky Way's outer halo. This collision superheats the gas, causing it to emit faint radio waves that astronomers first detected in the 1960s. By tracking these signals, scientists realized the Smith cloud isn't just any interstellar cloud. It's a high-velocity invader, carrying enough hydrogen to birth 2 million stars like our Sun. Yet, despite its staggering mass, it's mostly invisible, a shadowy leviathan revealed only through the distortions it creates in the fabric of space. The most tantalizing question is where it came from. Chemical fingerprints in the gas suggest it might have been ripped from the Milky Way's own disk billions of years ago, ejected by a close encounter with another galaxy, only to boomerang back. Others argue its composition is too alien, hinting at an extragalactic origin, perhaps a shredded dwarf galaxy or debris from the chaotic formation of the local group. Whatever its past, its future is certain. In about 30 million years, it will finally collide with the Milky Way's spiral arms, triggering a fireworks display of star formation as its gas slams into denser regions of our galaxy. This isn't just a one-off event. The Smith cloud is a reminder that galaxies aren't static islands, they're dynamic beasts, constantly feeding on intergalactic material like cosmic predators. Similar high-velocity clouds might be falling into the Milky Way right now, invisible to us until they ignite new stellar nurseries. Every time we study structures like this, we're glimpsing the hidden highways of the universe, where gas, stars, and even whole galaxies are in perpetual motion, locked in a dance that's been ongoing since the dawn of time. And the Smith cloud, it's just one player in this grand ballet, hurtling toward its destiny at speeds that defy comprehension. Most stars die quietly, fading into cosmic dusk, but LP 4365 didn't just go out with a bang, it became the shrapnel. This stellar survivor, a white dwarf hurtling through the Milky Way at 2 million miles per hour, is unlike anything else we've found. It's not just fast, it's a fragment of cosmic disaster, a piece of shrapnel flung into space by a supernova so violent it should have obliterated everything. Yet here it is, a rogue chunk of star guts racing across the galaxy with a backstory written in its very atoms. What makes LP 4365 so bizarre is its composition. Unlike typical white dwarfs, ashy cores of carbon and oxygen left behind when stars like our Sun die, this one's packed with oxygen, neon, and magnesium. Those elements are the fingerprints of a very specific kind of explosion, a type I supernova, the detonation of a white dwarf pushed past its limits. Normally, these explosions leave nothing behind, just an expanding cloud of gas, but this one, it barely held together, a charred remnant spat out like a bullet from the barrel of a cosmic gun. The violence of its birth explains its insane speed. When the supernova erupted, the explosion wasn't perfectly symmetrical. Just like a firework spinning wildly as it bursts, the lopsided blast gave LP 4365 a kick strong enough to escape its own galaxy. Imagine a grenade exploding. The shockwave doesn't just vanish, it hurls debris in all directions. Now scale that up to stellar proportions, where the shockwave flings a city-sized chunk of star core fast enough to cross the distance from Earth to the Moon in under 10 minutes. But here's the real mystery: how did it survive at all? Type I supernovas are supposed to be total annihilations, the white dwarf completely disintegrating in the blast. One theory suggests LP4365 might have been part of a binary system where both stars were white dwarfs. As they spiraled toward collision, one detonated early, blowing the other away half-cooked, a mangled piece of shrapnel still hot from the blast. The alternative, it could be the core of a star that only partially exploded, its outer layers blasted away while the heart barely clung to existence. What's certain is that this white dwarf isn't just racing, it's fading. The same explosion that launched it also superheated it to nearly 200,000 degrees, making it glow blue-white like a welder's torch. But as it streaks through space, it's cooling, its light dimming into oblivion. Eventually, it'll vanish entirely, a cold, dark bullet silently traversing the galaxy. For now, though, LP4365 is a cosmic accident turned time capsule. Every atom in its body tells the story of a star's violent end, and every mile it covers is a testament to the universe's raw, unfiltered power. It's not just the fastest white dwarf we've found, it's a warning from the cosmos, proof that even death isn't always final. Sometimes it's just the beginning of a much wilder journey. When two neutron stars collide, the universe doesn't just create a flash of light, it literally hurls treasure into the cosmos. Take GW170817, the first neutron-star merger ever detected. This cataclysm didn't just send gravitational waves rippling through space, it launched a tsunami of gold, platinum, and other heavy elements at nearly 30% the speed of light. That's fast enough to cross Earth's entire diameter in less than a second. The physics behind this cosmic jewelry store is staggering. As the neutron stars spiraled inward, their immense gravity stretched and shredded their surfaces, flinging ribbons of ultra-dense material into space. In the milliseconds before collision, tidal forces ripped apart these city-sized stars like taffy, creating a swirling maelstrom of neutrons. This neutron-rich environment triggered rapid atomic capture, forging elements heavier than iron in a process called R-process nucleosynthesis. Imagine a celestial smelter where cosmic forces compress and fuse atoms so violently they birth gold by the truckload, and we mean truckloads literally. Scientists estimate GW170817 ejected 10 times Earth's mass in gold alone, enough to gild every inch of our planet's surface 3 times over. The platinum output was even more ridiculous, clocking in at nearly 20 Earth masses. All this bling didn't just drift lazily away, it was accelerated outward in a bipolar jet moving at a quarter light speed, painting the surrounding space with the universe's most expensive graffiti. But here's the kicker, we're literally made of this stuff. Every gold ring, platinum necklace, or uranium fuel rod on Earth was forged in similar cosmic explosions. Without neutron star mergers, the periodic table would stop at iron, leaving our planet devoid of the heavy elements essential for technology and even life itself. The iodine in your thyroid, the xenon in car headlights, all forged in these violent collisions, then scattered across galaxies by their insane ejection speeds. What's truly wild is how recent this discovery is. Before 2017, astronomers debated where heavy elements came from. Supernova were the leading suspect. But GW170817's afterglow settled the debate. Its spectrum contained unmistakable fingerprints of lanthanide's rare Earth elements that only form in neutron-rich environments. That glowing debris cloud was a smoking gun, proving kilonovae are the universe's primary gold mines. Yet for all their destructive power, these events are oddly precise. The merger's ejector wasn't a random explosion, it followed finely tuned trajectories, with lighter elements like strontium flung wider while gold and platinum concentrated in tighter streams. This cosmic sorting system means some regions of space might be far richer in precious metals than others, like interstellar Klondike veins waiting to be mined. The aftermath plays out like the ultimate alchemical reaction. As the ejector races outward, it cools from billions of degrees to mere thousands, condensing into nanoscale gemstones. Some theories suggest these clouds might contain literal diamonds, carbon crystals forged in the explosion's heart, now laced with gold atoms like the universe's most opulent engagement rings. And because these mergers are rare, occurring maybe once per 100,000 years per galaxy, each one is a precious cosmic event, scattering its riches across space to be recycled into new stars, planets, and perhaps even civilizations. So the next time you admire a piece of gold jewelry, remember, it didn't come from a mine. It came from the wreckage of two dead stars hurled across the cosmos at unfathomable speeds, carrying the legacy of one of nature's most violent and beautiful creations. While most planets take months or even centuries to orbit their stars, TOI 2109b, a gas giant 6 times heavier than Jupiter, completes a full lap in just 16 hours. That's faster than one rotation of Earth. This exoplanet doesn't just orbit its sun, it skims the surface like a moth trapped in a deadly spiral around a flame, its atmosphere scorched to 2,500 degrees Celsius by perpetual starlight. What makes this world truly extreme isn't just its speed, it's the inevitability of its doom. Unlike Earth's stable, billion-year dance with the sun, TOI 2109b is locked in a death grip with its star. Tidal forces have synchronized its rotation so one side always faces the inferno, creating a permanent day of molten metals and night-side winds howling at thousands of kilometers per hour. But this cosmic equilibrium won't last. Every orbit tugs the planet incrementally closer, its path decaying like a satellite succumbing to atmospheric drag, except in this case, the atmosphere is the star's own gravitational fury. Astronomers estimate TOI 2109b has less than 10 million years left before it crosses the point of no return. Once it dips too close, the star's gravity will start peeling away its outer layers like an onion, stretching the planet into a teardrop of superheated gas. Eventually, the core will plunge into the stellar surface, triggering a final, violent splash, a transient brightening visible across interstellar space. It's a fate shared by many hot Jupiters, but TOI 2109b is the fastest we've found, making it a ticking time bomb on cosmic scales. The real puzzle is how such a massive planet ended up so close to its star in the first place. Gas giants typically form farther out, where temperatures allow ices to clump together. One theory suggests TOI 2109b might have migrated inward after gravitational tussles with other planets, like a pinball ricocheting through its system until it got trapped in this lethal embrace. Another possibility, it was born from the wreckage of a catastrophic collision, its debris coalescing unusually close to the star. For now, this doomed world serves as a grim preview of planetary evolution's endgame. As telescopes like JWST study its evaporating atmosphere, they're witnessing the final chapters of a gas giant's life where even the mightiest planets can't escape the universe's ultimate deadline. And every hour TOI 2109b survives is another revolution toward oblivion, a reminder that in the cosmos, speed doesn't always mean escape. Sometimes it's just the countdown to destruction. At the largest scales, the universe isn't just expanding, it's running away from itself. Galaxies billions of light years from us aren't merely drifting apart, they're fleeing at speeds exceeding 200,000 kilometers per second, vanishing into the void faster than light could ever hope to catch them. This isn't the steady, predictable growth scientists once imagined. It's an ever-accelerating exodus powered by something far stranger than gravity. Dark energy, the universe's most perplexing fugitive. Picture a loaf of raisin bread baking in the oven. As the dough rises, every raisin moves away from every other raisin, not because they're actively traveling, but because the space between them stretches. Now imagine the oven suddenly gets hotter, and the dough starts expanding faster and faster. That's the universe we live in. distant raisins galaxies speed away so rapidly they'll eventually disappear from view, their light too stretched by the expanding space-time to ever reach us again. This is the fate awaiting nearly every galaxy beyond our local group, not because they're moving through space, but because space itself is stretching beneath them like an unstoppable tide. The culprit behind this runaway expansion, dark energy, a mysterious force making up 68% of the universe's energy budget. Unlike gravity, which pulls matter together, dark energy behaves like anti-gravity, pushing space apart. The farther two galaxies are from each other, the more space lies between them, and the more dark energy exists to pry them apart. At a certain distance, this repulsive force overwhelms gravity entirely, triggering the exponential acceleration we observe. Here's the cosmic irony: dark energy's dominance is a recent development. For the universe's first 9 billion years, gravity had the upper hand, slowing the expansion. But around 5 billion years ago, as galaxies grew more distant and dark energy's push surpassed matter's pull, the expansion shifted gears. Now we live in an era where distant galaxies recede at speeds approaching light itself, their light redshifted into oblivion by the stretching space between us. The most unsettling part: we have no idea what dark energy actually is. It could be a property of space itself, as Einstein once theorized with his cosmological constant. Or it might be a dynamic field, changing over time, a possibility that raises even wilder scenarios, like a future Big Rip, where dark energy tears apart galaxies, stars, and even atoms. What's certain is that this acceleration isn't just a footnote in cosmology, it's the defining trait of our universe's fate, a reminder that even the vacuum of space isn't empty. It's alive with a force we can't see, can't touch, but whose influence is rewriting the cosmos at speeds beyond comprehension. From neutron stars spinning with dizzying ferocity to hypervelocity stars flung like cosmic slingshots across the galaxy, the universe is packed with objects that defy our very understanding of speed. The fastest pulsars whirl at nearly a quarter the speed of light, their surfaces moving so fast that time itself distorts under the strain. Hypervelocity stars like US 708 rocket through space at over 1.6 million miles per hour, banished from their homes by the gravitational fury of supermassive black holes. And then there are the relativistic jets, beams of superheated plasma screaming from black holes at 99% light speed, stretching across thousands of light years like cosmic laser beams. But here's the real mystery: if these are the speed demons we've already found, what else is out there? Could there be objects moving even faster? Particles nudging closer to light speed than we've ever measured, or rogue planets catapulted through intergalactic space by forces we can't yet imagine? The universe loves to surprise us, rewriting the rules just when we think we've seen it all. So what do you think? What undiscovered speed demons are still lurking in the cosmos, waiting to shatter our expectations? Let us know in the comments, and don't forget to like and subscribe for more deep dives into the universe's greatest mysteries. The cosmos is full of secrets, and we're